when any number of objects collide, they conserve momentum, but we're going to limit ourselves to cases in which only two bodies collide and interact. So when two bodies collide and interact, we know from Newton's third law that the force that object A exerts onto object B is equal and opposite to the force that object B exerts back onto object A. If we multiply both sides of this equation by the time for which the collision lasts, now we're saying that the impulse delivered to object B is equal and opposite to the impulse delivered to object A. And impulse is the same thing as change in momentum. So the change in momentum for object B is equal and opposite to the change in momentum for object A. And that leads to a statement that says the total change in momentum for the whole system is equal to 0, which is a way of implying that momentum is conserved. So another way to say that is the total initial momentum for any system is equal to the total final momentum of that system. Although you have to satisfy two conditions for that to be true. Here are the two conditions. One, the collision or the system has to be isolated. And the second criteria is that the system has to be closed. Actually, let's start with defining what we mean by closed system first. That means no mass gets in or out of the system. Your body is certainly not a closed system. The planet Earth isn't quite a closed system, right? There's a few meteors that collide every now and then. Once in a while we send people to the moon and so on. So in this system, if the two objects collide with each other and a little piece were to break off and go flying away, then the system would not be closed. Okay, so we're going to limit our study to closed systems. An isolated system is one in which internal forces may exist, but there are no external forces. So an example would be when these two gliders are sliding across this surface, we're going to assume that the friction is equal to 0. But if that weren't the case, when they collide, the collision between the two, the force that A exerts onto B and the force that B exerts back onto A, is an internal force to the system. But if there was friction between either the two blocks and the ground, then there would be an external force acting on the system. Although we could include the entire Earth as a third body in our system, and then friction would become internal. But we want to limit ourselves to two-body systems, so we want to ignore things like air resistance and friction and other external forces. So as long as we satisfy those two conditions, as long as the collision involves an isolated and closed system, then momentum is conserved, and the total initial momentum in the system has to equal the total final momentum. So another way to state that is that the mass of object number 1 times its initial velocity plus the mass of object number 2 times its initial velocity has to be equal to the mass of object 1 times its final velocity plus the mass of object 2 times its final velocity. Notice that I'm using the symbol U for initial velocity, and I use the symbol V to represent final velocity. So we're no longer going to use the subscript 0 to mean initial velocity. We'll replace that with the symbol U. Well, when two bodies collide with each other, maybe object 1 is moving to the right. In our first example, object A moved to the right, object B moves to the left, but you could also have a case in which object number 1 moves to the right at a high velocity and object number 2 is moving a little slower, so object number 1 overtakes and collides with object 2. As long as that's a closed and isolated system, momentum would also be conserved in that case. So there are a few different possibilities. When object number 1 hits object number 2, maybe this part is covered with half of a Velcro strip, and this is covered with the other half so that the two stick together when they collide, or maybe not. Maybe object number one has a rubber bumper on it, and object number two also has a rubber bumper on it, so when they hit, they remain separate. Another possibility is when they hit, they could have a spring between the two of them, an ideal spring. So for a moment, when they make contact with each other, the spring is compressed and some mechanical energy in the form of kinetic is transferred into elastic potential energy in the spring, but then the spring ultimately rebounds back to its original shape, and the two go flying apart at different velocities. So that can convert back into kinetic energy. And if there's no mechanical energy converted to wasted thermal energy, then we would describe the collision as elastic. But there are some cases where objects collide. There's not a spring, and maybe they're initially moving at two different speeds. Object one overtakes object number two. And then for a moment, they're in contact and they collide. And then ultimately, object one maybe bounces back in this direction, and object number two travels at a different final velocity in this direction. But we notice that both of them have some lasting deformation due to the collision. And whenever that happens, there will be some amount of mechanical energy that's converted to wasted thermal energy. So we need to name collisions based on these different possibilities. So one, we can ask the question, do the objects stick together when they collide? And we could ask the question, is there any thermal energy that's generated in the collision? So we'll make a graphic organizer for this, and we'll name three types of collisions. One is called perfectly, oops, sorry about that. Try again. Perfectly inelastic. Another type of collision is just inelastic. And the third type of collision is elastic. In a perfectly inelastic collision, yes, the objects stick together, and yes, some mechanical energy is converted into wasted thermal energy. In an inelastic collision, mechanical energy is also converted to thermal, but the objects do not stick together. Two objects come in, collide, and remain two objects after the collision is done. Same thing with an elastic collision, they do not stick together, and additionally, there is no conversion of mechanical energy into wasted thermal energy.